All right, we started getting some. Okay, I think we should be starting. I see the attendees number going up. It is my great pleasure to present Professor Jianfeng Lu, who is currently a professor of mathematics, physics, and chemistry at Duke University. Before joining Duke University, he obtained his PhD in applied mathematics from Princeton University in 2009. And he was a Quran instructor at New York University from 2009 to 2012. He works on mathematical analysis and algorithm development for problems and challenges arising from computational physics, theoretical chemistry, material science, high-dimensional PDEs, and machine learning. His work has been recognized by a Sloan Fellowship, an NSF Career Award, and the 2017 IMA Prize in Mathematics and its applications. Please, Jianfeng, you have the podium.
Thank you. Thanks for the introduction. It's a really great pleasure to have the opportunity to speak here. And thank you all for joining from different parts of the world, especially during this difficult time. So today I'll be sharing with you some of our recent works in trying to overcome the difficulty in solving eigenvalue problems in very, very high dimension. So this has been going on for a couple of years, and it's a real great pleasure to have the collaborators contribute a lot to the work. So including Jiequn Han from Princeton, and Yingzhou Li, who is a postdoc at Duke, but will soon join a faculty position in UC Berkeley. Wang, who has recently graduated, and Zhou is a current student at Duke. So the problem that we're considering is naively simple in a way. So it's essentially just that if we were given a matrix, the matrix coming from a discretization of a PDE, and we're interested in some extreme eigenvalue and corresponding eigenvector of the matrix. And of course, by shifting without loss of generality, we can assume that we are just interested in largest eigenvalue, and also our largest eigenvalue is positive. Of course, now the immediate question you may ask is that why I'm talking about this, because of course we have over the years, this is a central topic in numerical computations, and many, many methods has been developed. I just list a few here. But the question that we are considering has some new kind of challenge. And the challenge is essentially coming from the problem, the fact that we're considering problems where this discrete matrix, the dimension of the matrix, or the N here, is super, super large. And as a result, we cannot hope to store this matrix in the memory, so that we also need to compute the entries of the matrix on the fly. As a result, that the access or evaluation of the matrix entry can be also expensive. So given these challenges in mind, the method that we are hoping to kind of develop must use some kind of compressed representation of vectors, because we cannot, we are interested in the problem where N is super large, like 10 to the 20, so that it's impossible to represent the vector as it is in the memory. And also we want the method to be really efficient, not only fast, but also trying to reduce the number of matrix element access. So that's the motivation. And you may ask where these problems come from. Of course, they can come from many, many different areas, for example, data science. But the main motivation that I'm interested is from the many-body Schrödinger equation from the computational physics or chemistry. So this is the Schrödinger equation that describes the wave function, the ground state wave function of a many electron system, where this x1 to xn denotes the position of electrons. And if you haven't seen this equation before, this is the kinetic energy of the electrons. This is interaction with the external potential, maybe coming from the nuclei. And this is the Coulomb repulsion, that electrons do not want to stay together with each other. So you can see that this is eigenvalue problem. And the challenge really comes from that this is a wave function. This is a function that depending on n coordinates, n positions, and each of them lives in 3 dimensions. So that this is really a function that lives in R3n. And as is well known, that we have the so-called curse of dimensionality. So if we use some conventional discretization scheme for this function, if we put in some grid points per dimension, then the number of grid points we need is exponentially depending on the system size. So very quickly, the matrix dimension goes very fast. And just give you some example, even for very small systems, for example, the water molecule in a not so large basis, the matrix dimension is already 10 to the 9. And for some reasonably larger problems like chromium dimer, the matrix dimension can be easily 10 to the 20. Okay, so our challenge or the motivation is really how to deal with such like so-called 4CR eigenvalue problems on the computer. Okay. And most of these works in, my interest in this area was motivated actually by one paper that was published about 10 years ago by the group of Ali Alavi, who is a theoretical chemist then at Cambridge. So they developed a method called 4CI QMC. The detail of the method is not that important, but if you're interested, it's kind of like a diffusion Monte Carlo in the so-called second quantization space. And let me show you an example. So that this is an example done by my student Zhou Wang. So it's a physically, it's a 4x4 Hubbard model on the 4x4 lattice with 10 electrons. The matrix dimension is not that large, it's 10 to the 6, so it's about 1 million. And you can see here the walk clock time versus the accuracy. So these curves are like our traditional methods, the power iteration, Lenshaws, and something like slightly improved than that. And this is curve that produced by the 4CI QMC time methods. And you can see that even like on this time scale, you cannot even see the initial realization of the method. It almost already reached to the accuracy level. Okay, and it's a Monte Carlo algorithm. It's a stochastic method, so that there are some fluctuations. But the idea is that if you average long enough, then this Monte Carlo average will decay. And in fact, the reason that this being so fast is just because that, for these methods, each iteration is very, very fast. Okay, so let me just give you some, without going into very details, let me give you some understanding of these methods. So one can frame all these, put all these methods into a single frame, what we call the inexact power iteration. So this is, like power iteration is perhaps the most naive method that you will think if you want the largest eigenvalue, right? It's just each step, each iteration, you multiply the matrix with a vector. So it's inexact. So we're thinking of some kind of operation that can approximate the matvec, the matrix vector multiplication, but with some error. And this error could be deterministic or stochastic, which we denote by C. And we also want to, remember that our problem is super large, so that we want to keep the vector sparse, so that we denote it by some m parameter to control the sparsity of the iterations. Okay, and actually, in under this framework, you can put all these methods into here. So, for example, the 4CI QMC is essentially a stochastic interpretation of the matrix vector multiplication by some particle interpretation. And there are some also works that develop in applied math literature and sort of fast randomized iteration that developed more recently. I'm not going to all these things, but there are many, many others also developed in the computational physics literature and chemistry literature as well, also in machine learning and so on. And actually one can prove of these methods that the convergence analysis can be done. So, essentially they converge like the power iteration, but plus some error. And the key of these like modern power iteration methods is that one hope that each iteration is much, much cheaper than the conventional one. So that while you take the number of iterations you take is about the same, but because each iteration is very fast, so that you can get a very super fast convergence. Okay. So, is there any questions so far before I go to like the main part of the talk?
No, I don't see any.
Okay,
no,
great. So everything's clear so far. All right, so after we analyze this framework and prove convergence, try to understand all these methods developed in chemistry literature, so on, we are asking ourselves whether we can do something slightly better. And then we realize that maybe actually we don't want to really stay with the power iteration framework. Like, all these methods are essentially modifications of power iteration, or more generally Lenshaws type of iterations. Okay, and so we're thinking about other possibilities. And I mean, we find that there is optimization for reformulation of the eigenvalue problem. And this has been known like long before our work. But I mean, I don't think many are utilizing this for the eigenvalue problems. So this is, I mean, remember that our A is symmetric. So this is essentially a best rank 1 approximation of the matrix A, I mean, in the Frobenius norm. Right? This is our objective function. And you can easily convince yourself after, I mean, looking at it for a while that, I mean, the best optimal choice of X is indeed a scale version of the leading eigenvector. I mean, you just need to do eigenvalue decomposition of A and to see that. And you can also find the gradient and Hessian computed very easily. I mean, this is just the 4th order polynomial in terms of X, so that this is a really easy function. And the gradient tells you that all the stationary points of this objective function are the eigenvectors and eigenvalue, I mean, corresponding eigenvalues are kind of given by normalization. I mean, this is actually the reason that we assume the first leading eigenvector is leading eigenvalue is positive, so that we can take a square root. So these are all the stationary points. And you can also look at the hashing of these stationary points. And you discover that all the eigenvectors except the leading one that we are interested in are all saddle points and are strict saddle points so that they have descending directions. And the only local minimizer of the problem is actually the global minimizer of this objective function. Okay, so in other words, there was no spurious local minimum. So this is a good news for optimization because, I mean, this is a landscape of this 2x2 problem. And because, I mean, if you can guarantee that it goes to a local minimum of the method, then we're done. While, of course, this is a non-convex function that we know that if we, for general non-convex function, if we want to find a global optimum, this is much harder. And I mean, let me mention that this is actually the special, I mean, it is kind of like a special feature of the eigenvalue problem. And there are existing of other reformulations like the OMM or trace penalty reformulation that also have this property that the energy landscape is nice in the sense that all the local minimizers are global minimizers. Okay, but we are sticking this one because it's easy, it's just a 4th order polynomial. And now, I mean, for optimization, right? If we have open our book of numerical analysis, I mean, there are tons of methods that we can use. So maybe the first method that comes into mind is the gradient descent. Okay, we just add to iterate some scaled version of the gradient at each step. And if you just write down the gradient and write out explicitly, you see that this is actually a kind of power iteration, right? So that this step, you just multiply the matrix to the vector. And this is a normalization thing. This is a Lagrange multiplier, essentially. And as we discussed for the power iteration, I mean, so this is very easy to analyze. But the problem is that for our setting, because the matrix dimension is so large, so that this is very high cost each step. Okay, and now you can see, I mean, these days because of the rise of machine learning, so that I mean, people are all familiar with that. If these problems can be accelerated, we don't really need the full gradient, exact gradient. We can do approximation of the gradient to this problem, so which is the so-called stochastic gradient algorithm. And I want us to make sure that the expectation of this stochastic gradient is not too far away from the true gradient. And the advantage being that the approximated gradient is much, much cheaper to evaluate. Okay, so this is in fact very similar to the FCIQMC method, I mean, the idea. So because in each step, we're replacing this very expensive matrix vector multiplication by something much cheaper. Okay, now, I mean, we think that actually there are other possibilities of doing an optimization, right? And what we realize is that for our particular problem, perhaps the most suitable way to think about or to use the method to use is the coordinate descent algorithm, for which at each iteration, we just change one coordinate of the vector. So that this is EJ. So these are the standard bases in the Euclidean space. Okay, and this is the partial derivative of the objective function only in that direction. And obviously this is, I mean, at each iteration, because we only change one coordinate, this is very fast. And also compare with the stochastic gradient, it also has advantage that we can choose the step size so that to make the descent stable. While here, because each time you are doing some random direction, you may not be able to make sure that energy is always descending. Okay, if you're interested in the coordinate methods, of course, Steve Wright wrote a very nice review paper a couple of years ago. I mean, mostly for applications in machine learning. And now for coordinate method, a general kind of description of the algorithm is just given by the following. So for each iteration, we use our information of x and z. I mean, z is essentially a version of a times x. So because, I mean, remember that our gradient have this matrix vector multiplication, so that we need to keep track of it, and in the efficient fashion. So that's the use of the z. Okay, so given this information of the gradient of the current iterate, we want to pick a coordinate, and then we want to update the coordinate value and keep the other coordinates the same, and we go on, right? And as I said, already mentioned that this is just a coordinate update rule of a times x. And you may realize that we also need a norm of x, but I mean, the same thing can be done so that we can also do a coordinate update of the norm, which I'm omitting here in the description. So the question here is, of course, how to pick the coordinate and how to update the coordinate to make it efficient. You can do cyclic updates, you can do random coordinate picks, and these are actually not going to be quite efficient for our problem. And so the thing that we use is that, first of all, I mean, because locally the gradient still gives you the information of in which direction that the objective function is changing the fastest. So the coordinate pick strategy we are going to try to use is actually use the local gradient information. So we want to pick the coordinate such that the absolute value of the partial derivative is largest. And then a nice feature of our problem is that because our objective function is essentially a fourth order polynomial, so that after we fix a direction, we can, I mean, usually the line search cannot be easily done, right? And you can need to do some backtracking and things like that. But because our problem is just a fourth order polynomial, so that actually we can solve the line search exactly. It's just solving a fourth order polynomial equation. And we can do exact line search after the coordinate pick. Okay. So combine these things together so that this is the method that we propose. It's a greedy coordinate method. So that at each step, we pick the largest partial derivative direction, and then we do a line search. I mean, one can prove theorems. I'm not going to, I mean, due to time, I'm not going to list these results, the regressive theorem results, but one can prove local convergence, I mean, with a rate independent of dimension. Remember that the dimension of a problem is really, really large, so that we really want a convergence independent of dimension, so that this is nice. And one can do something more greedy. For example, actually, one can swap these two steps. I mean, one can first do a line search and then do what they call this pick. But I mean, in practice, we find that this is the best compromise. And well, I mean, let me also mention that we do not need to be fully greedy. We can do some stochastic choice of the coordinates and to increase robustness, especially if you want to do parallel computing when you want to choose multiple coordinate updates at one each iteration. Okay, so this is a theorem. I mean, I mentioned already that, I mean, so that the convergence rate is independent of dimension. It only depends on the condition number of the problem. Okay, and let me not dwell too much on this. So let me just show you by a numerical example that I think there is something interesting about this formulation of the problem. So this is a toy problem. It's a matrix dimension of 5,000 by 5,000. And there is a gap between the first eigenvalue and the rest of the eigenvalue. So all the rest of the eigenvalue is bounded between negative 100 and 1, while the first eigenvalue is negative 108. And we see, I mean, so that if we do this original matrix, and we compare with the power iteration, or there is an algorithm called coordinate power iteration, and this is a graded coordinate descent algorithm, we see that actually the iteration number is, I mean, the coordinate method is not really, I mean, kind of faster than the power iteration. I mean, the power iteration indeed has a lower iteration number. But in each iteration, because the power method has to multiply the full matrix on the vector, so that each iteration is more expensive. And as a result, I mean, in all, the coordinate method actually has a 6 times speed up. And what's more interesting is that seems, I mean, for the problem, even if we shift it, right? So that essentially the problem is not changed at all. I mean, just because we just shifted the matrix by a constant diagonal matrix. But because the method has some kind of different condition numbers corresponding to our optimization framework and the power iteration. The power iteration is the gap divided by the kind of the spread of the spectrum. And you see that the iteration number of the coordinate method doesn't change much, while the power method has changed a lot, so that the speed up is even faster. So it seems that in some situations that, I mean, doing the optimization framework is actually gains a lot. I mean, not only from the coordinate descent, but also from the different iteration, the convergence of iterations. Okay, so And of course, the main advantage of this coordinate method is that we can update the entries of the vector according to its significance. Because each time we pick, we're not like doing random pick or doing cyclic pick. We try to choose the coordinate, which actually maximizes the effect. And you see that in this figure, the blue curve is the number of the coordinate updates for each coordinate. And the red curve is actually the magnitude of the final eigenvector. And you see indeed that it's correlated very well that the number of updates is used is kind of for the most important entries in the final eigenvector. And this is actually the reason that to reach convergence, we actually don't even need to visit all the eigenvectors, all the coordinates, so that in this plot, there are many coordinates that actually haven't been updated even once, but already one can reach to a very high accuracy level. That's good enough for the chemical problems that we're interested. Okay, so now before I go into the real chemistry applications, any clarifying questions that I can answer?
No, it's fine.
Okay.
You can go.
So let me go to more real interesting chemical examples. Okay, so let me mention, just to remind us again that we're interested in the many-body electronic Schrödinger equation. So that this is the equation I wrote. And as I mentioned before, that the problem is that the matrix dimension grows very, very fast. So it's actually combinatorics fast. Because of symmetry, so it's not really the exponential, it's kind of a combinatoric, it's a choose of the number of grids that we put in each direction divided by number of electrons. We choose the number of electrons, okay? And so on the four-sided discretization of the Hamiltonian, the Hamiltonian consists of two types of terms. This is like a one-body term, and this is a two-body term. So if you haven't seen this before, this is second quantization representation of the Hamiltonian. But the point that I write this down is just to tell you that actually, one feature of this kind of Hamiltonian is that the Hamiltonian is actually really sparse. You can see from this representation is that because the Hamiltonian only contains these two-body terms, in principle, these n electrons can interact together, but the physics law tells us that they only repel each other by the Coulomb repulsion. So that's the reason that the Hamiltonian is actually fairly sparse, okay? And now for this problem, there was additional difficulty, than the toy example that we mentioned before. Because now the matrix times the vector, we have a vector, right? And because the dimension is so large, so remember that we're since interested in the problem of the matrix dimension is 10 to 22. So there's actually not possible to store these vectors in the memory. So and the reason that even though that the Hamiltonian is indeed sparse, but each row, it may also have a million entries. And when I multiply this matrix with this vector, it increased the non-zero entries of the X by a million times, okay? So that it's almost impossible to store Z. And we need some compressed storage, or in other words, we need some truncation of the Z when we believe that the entries are not important. And also because of this, right? So when we pick the coordinates, before, if the matrix dimension is not that large, we can go over each direction and try to pick the best coordinates we think. But now this even becomes inefficient. So we need to use some heuristics to do that. And so that the final algorithm is kind of like this. So there are changes highlighted in the blue. So before, we are just looking at each entry of the gradient to make the largest pick. But now, because we do not really want to go over all the entries, like there were 10 to 20 of them. And we're only looking at like some neighborhoods of the last updates that we have used and looking at all these coordinates so that this is manageable. The number of that is manageable. The line search, we can do it exactly as before. And then when we update Z, so what we do is that, so if the coordinate is updated, then we need to calculate it. And if the coordinate, but if the Z entry is really small, or that, the matrix, the Z is not really in the entries that we think is important from the previous iteration, then we just set it to be 0. So we keep it sparse, okay? And notice that because, the rule that we designed, it looks complicated, but the reason we designed this rule is that we just want to make sure that for all the entries that our X vector is non-zero, we want to make sure that the corresponding Z is also numerically accurate. The reason being that the inner product of X times Z, you see that is X transpose HX. So that's the risk value that we are interested in. And because we're interested in eigenvalue, right? So that this is this size. So because in the end of the day, we're interested in risk value. So that's why we want to make sure that, this is our z-mate vector, h times x. We want to make sure that at least when x is non-zero, that the entry of z is accurate. So that even though we do a lot of truncations and approximations, but still we can get a numerically accurate really quotient, given the x. So we can guarantee that the estimate of the eigenvalue that we get are indeed the upper bounds of the smallest eigenvalue. Okay. So let me show you some numerical example. And for all these comparisons, we are doing the chemistry problem. And just to make sure that we are on the same page, so that all these Hamiltonian are generated by a Psi4 package that we use. And we compare with many of the state-of-art algorithms that use in the chemistry and the physics literature. So this is an improved version of the QMC that from the NECI package. And there is a heat bath CI package. This is kind of like you incrementally increase the problem of size of a problem by smartly choosing like which coordinate that you want to put in. And there is a method based on tensor networks or matrix product state called DMRG. And this has been also applied to chemistry problems, and we're using the block package for doing that. And this is computation environment. And the algorithm, actually the main bottleneck is memory. So because the dimension of these things grows exponentially, so that even for like small molecules for chromium dimer, we already need to use 100 gigabytes. Okay, and then if we want to do larger problems, then the memory is a major kind of bottleneck. Okay, so this is a comparison result. So the first comparison is the water molecule. And the problem is about 10 to the, sorry, let me close this. The problem is about 10 to the 8, okay? And you see that this is a comparison of our method, which is the yellow curve. You see it's very stable because of the coordinate descent algorithm. We can always descend the energy. And it's also very fast compared with other methods. So that this is the HCI. The problem for HCI is that it cannot go to very large kind of truncations because, the memory concern, because the memory limitation. It uses the dense arithmetic of the matrix vector multiplications and so on. And the DMRG method can go high, but it's not as accurate as our method given the same walk clock time. And then this is the Monte Carlo problem, the Monte Carlo methods. They're fast, but the issue of the Monte Carlo method is that they converge quite slowly because you need to average out the fluctuations like 1 over root n. And so that you see that compared with these deterministic algorithms, the eventual convergence is much slower. One interesting feature I want to point out is that this matrix dimension of this problem is 10 to the 8. And in fact, to reach to a so-called chemical accuracy, 10 to the negative 5, we only need to revisit less than 10% of the coordinates. Okay, so that we don't, so this actually tells us the efficiency of the coordinate pick strategy. A lot of coordinates, it remains to be 0. Okay, and this is like a feature of the problem that I think which makes the coordinate methods really, really useful for these chemistry problems. Okay, and similar observation was also kind of made in other problems. So this is a slightly larger problem. It's a carbon dimer, 10 to the 10, and you see a very similar trend. The slight difference, the behavior of the Fourier QMC is due to the initial condition. The initial initialization has a slightly wrong symmetry, so that the Monte Carlo method suffers a bit of fluctuations in the previous iterations. But eventually the behavior is almost the same. And similarly for nitrogen dimer, which is a slightly larger problem, is 10 to 11. Still, like you can see the coordinate method that we develop beats all the methods, which is state-of-art performance for these problems. And we can also produce the binding curve so that this is a nitrogen dimer. So depending on the distance of the atoms, of the two atoms, nitrogen atom, this is energy, associated energy of the nitrogen dimer, and this is a bonding curve. And from the chemistry intuition, actually, the problem becomes more and more difficult when the nitrogen dimer is more stretched, okay, because the breakdown of the mean field approximation. And you indeed see that, the number of the coordinates that we need to include actually increases as the distance of the nitrogen dimer increases to the 10 to the 7. But still, it seems that the algorithm, even though for these tough situations, what chemists would call the strongly correlated problems, our algorithms still perform quite reasonably well. And remember that there was this epsilon truncation parameter that we use for truncate the vector z. And this plot shows the performance of the algorithm or the error of the algorithm related with this epsilon parameter. And the basic message is that the behavior is quite reasonable. It's very stable so that there is no magic in tuning the parameter. So, I mean, the better accuracy you want, the longer time that you need. Okay, so that there was a trade-off here. And last, I mean, this is a very challenging example. This is a chromium dimer, and the matrix dimension 10 to 22. And even though, I mean, we can see that the method that we are proposing, the CGFCI, can still perform quite well, and it reaches the best variational result. And of course, for this problem, we don't really know the exact results, so that we use the perturbation and extrapolation kind of results from these methods to predict the accurate value. Okay, but remember that our method is variational and it reaches the state-of-art performance. All right, so I'm finished with the coordinate part. So I think there was a question, right?
Yes, there is one question says, can you comment why your scheme will not encounter a circular situation in the process of the gradient descent iteration? This is one question. And there is a second, but do you want to answer it?
Yeah. So if I understand correctly, the circular means that the energy is not going down, so that we are just circling on the energy level. But because, I mean, we are doing descent and line search, so that each iteration, we guarantee that there is energy is going down if there is no truncation, no approximation. But of course, after approximation, this is not guaranteed. But I mean, we don't have any theorem to say that the energy is indeed monotone, I mean, after truncation. But it does seem that in practice, what we realize is that the truncation of the z vector does not occur that much. I mean, one reason for that is that we actually do not, so z or these vectors are only used as heuristics in picking the coordinates. And after the coordinates picked, we are still trying to do line search. But of course, I mean, we may still be stuck because maybe we are picking the wrong coordinates because our z is so bad, but it does not seem to occur in practice.
Okay, thank you. And there is a second question. Sometimes the ISFCI-QM method has an immediate and steep minimum. What is this due to? And would it not be an ideal strategy to recognize this minimum and stop?
Yeah, I mean, the reason for that is that this is a Monte Carlo algorithm. So that each time, I mean, each iteration, you essentially just output a random number. And then by chance, I mean, so that if you average a lot of numbers, then by chance that you may be able to hit a value that is very close to the true answer. But the problem is that, I mean, in the calculation, we don't really know the true answer, of course, ahead of time. Otherwise, we don't need to do that. And then there was no way to tell, like, I mean, given just sequence of the random numbers, that which one you should pick to stop. Okay, so I mean, indeed, there could be some chance that if you know the true answer, that this is very close, but there was no way to tell that, and there was no way to stop. So one has to rely on the Monte Carlo average convergence.
Mm-hmm. Okay, thank you. I think
okay.
It was
so let me proceed to the second, second part of my talk, which is shorter. So I talked about CGFCI approach, and I mean, it's very promising, and we see that it achieves very good result compared with the existing method. But still, I mean, we are suffering from really the curse of dimensionality. Even though that this is a very efficient way to deal with the problem, but because of discretization that we start with, putting the many-body shielding equation in the 4CI problem, the dimension of the problem is exponentially growing. And we can see from the previous examples, for example, for the chromium dimer, we are really dealing with a matrix problem with dimension 10 to 22. And this will be much, much larger, for example, if you want to go to chromium 4. And it's almost impossible. So one thing that, I mean, to kind of overcome this problem is that, well, the starting point of all these 4CI approach is essentially a traditional discretization of the many-body equation, a very high dimensional space. So that's why we face the curse of dimensionality. To overcome this, and maybe inspired by the recent success of deep learning or neural networks, one hope is actually without using the linear parameterization of these things, like using a basis and expand the wave function in the basis, which is a linear parameterization, we may try to use the so-called nonlinear parameterization. And these methods have been tried and developed in the community. For example, there was this famous tensor network method, and it's been, as I mentioned already, the MRG method. It's been originally developed by Steve White in 1992. And then there was 2D version of that by Verstraete and Siraj in 2004. I mean, there are many, many more references. I mean, due to time, I will just list some representative ones. And also more recently, because of the popularity of deep learning, people obviously have trying to parameterize the wave function using neural networks, starting from the like a paper, very popular paper by Carlio and Troyer back in 2017, and a lot of follow-ups of that paper. So most of these methods, I mean, the popular approach that is based on the so-called variational Monte Carlo. So it's very different from the power iteration or from iterative methods in a way. So because now the idea is that you define this weighted quotient. I mean, remember that, I mean, for the physical problem, we want the smallest eigenvalue, so we minimize this. And now the theta is the collection of parameters that you use in the wave function ansatz. And then you start to minimize this, just as in the sense of supervised learning, right? You're just doing stochastic gradient descent, for example, trying to do the optimization of theta, trying to lower the energy, and then the psi of theta, I mean, this nonlinear parameterization is the approximation of the ground state. And when after we finish this coordinate descent algorithm and we're trying to get very interested in neural networks, parameterization of the wave function, we ask ourselves a very basic question in a way. So because these methods are really different from power iteration, or in the computational physics context, these methods are usually called diffusion Monte Carlo. I mean, remember the force QMC is a diffusion Monte Carlo approach. And the question we ask is that, is there a possibility to do diffusion Monte Carlo? I mean, combined with these nonlinear parameterizations, for example, the neural networks. And this is a method that we came up with, and I just want to share with you. I mean, it's still in the preliminary stage where a lot of new developments are needed, but I think it's promising, and that's why I want to share with you. And so we consider the eigenvalue problem, and we consider a very general, I mean, this problem can be general and it can be even nonlinear, so that it can be a semi-linear elliptic operator. So this is a diffusion part, second order part of the operator. This is a drift part of the operator, and then there was semi-nonlinearity. And now one can write down the corresponding parabolic evolution equation for this eigenvalue problem. It just evolves in time. And you see, of course, if U is already eigenfunction, the evolution, I mean, then this part is 0, so that the evolution in time is stationary, right? So that the eigenvalue and eigenpair of this operator is a stationary point of this evolution. And so if we denote the backward propagator as this pt lambda, okay? And because the eigenfunction is invariant, so we can come up with some kind of loss function to look at the discrepancy between the initial guess of the eigenvector psi and its evolved version under this parabolic equation after time t. And we're trying to, because the eigenfunction are the stationary points, so that for eigenfunction this is 0, and eigenpair with a correct corresponding eigenvalue, so that the idea that we want to do is to minimize this loss function and to find the eigenpairs, okay? And of course, at this point, I mean, this parabolic equation is still in very high dimension, right? So that is almost impossible to solve. And the idea that we have, I mean, our method is built on the approach by Jiequn Han, my collaborator, with Anouf Jensen and Wei back in 2018, the so-called deep learning BSD approach trying to solve for the parabolic equation. So, I mean, I'm running out of time, so let me be kind of brief here. So the basic idea is that you can, I mean, using stochastic calculus, using the forward-backward SD representation, you can write down the parabolic equation as a diffusion equation for the position with a backward stochastic equation for the unknown function u. And this is essentially just application of Ito's lemma, okay? And of course, I mean, solving the SD is easy, right? I mean, so it's much easier than solving a PDE in high dimension. I mean, SD is essentially ODE. The catch is, of course, that we don't really know these functions u, I mean, in this SDE, so that we need to kind of, I mean, this is a circular problem, right? We need to know these u's first to solve the u. Well, I mean, remember that we are just interested in consistency, right? So the idea is that we replacing these unknown quantities by a parameterization, a nonlinear parameterization, for example, the neural network. And then we use the loss function, I mean, like this is exactly the discrepancy term that we had before, this is a penalty of the gradient and with the calculated gradient of the neural network of the wave function. And we use this loss function to enforce inconsistency. Okay, so I don't have time to go into details, but let me just show you some numerical results. And these are numerical results, I mean, in 10 dimensions. Okay, so it's not super large yet. I mean, we're still trying to explore, I mean, more realistic examples, especially with symmetry of the quantum system. But for these 10-dimensional problems, this is a double well potential. So that actually the first and the second eigenvalues are kind of close. And of course, I cannot visualize functions in 10 dimensions easily. So that this is actually a histogram of the function. So that this is the value of function, and this is like what's the density of the function takes that value. And you see that the neural network approximation fits the true value very well. I mean, it's almost non-distinguishable on this scale. And also the same thing is true for the second eigenfunction. And this is a convergence plot of the training process. And let me mention that actually, because we are just enforcing this consistency, so actually the method, I mean, with right initial condition, we can also approximate second eigenfunction, as you can see here. And this is a pre-training phase that we fix the eigenvalue and we only train the eigenfunction. Okay. And now similarly, I mean, we can also get very good performance for nonlinear Schrodinger equations. So that this is a cubic Schrodinger equation. The left panel is in 5 dimensions. The right panel is in 10 dimensions. And I don't know any traditional methods can do this. I mean, can solve this eigenvalue problem for cubic Schrodinger equation in 10 dimensions. And I mean, for neural networks, even though like the accuracy is not machine accuracy, this is the trouble for machine learning as always. I mean, we get something like 10 to the negative 3, 10 to the negative 2. But still, I mean, you see that on the eyeball level, you cannot really tell discrepancy. And also the training curve, I mean, goes down very nicely and reasonably well. Okay. So let me stop here. I think I'm about up to time. So I tell you 2 things today. I mean, one is that some of our recent work trying to use the Cohen descent algorithm to accelerate the large eigenvalue calculations, I mean, with applications in quantum chemistry, especially in 4CI. And then also some preliminary results that we obtain in using the diffusion Monte Carlo type algorithms with using the neural network ansatz and wave function. We are currently trying to extend these things in several directions. For example, trying to do excited states, and by incorporating the symmetry and more realistic problems from many-body quantum mechanics, and also trying some machine learning approaches for solving other high-dimensional PDEs. Okay, so if you're interested, this is a reference. I think these slides will be available online. And now let me leave here with this advertisement of this conference next week. That is inaugural conference of the mathematical and scientific machine learning. It's supposed to be in Princeton, but now, of course, everything is virtual. And if you're interested, you can you can Google MSML 2020, and you can find a webpage, and you can try to register. Okay, thank you.
Okay, thank you very much for Professor Lu. Are there any questions, any new questions that came up? No, as far as I can see. While we have 2 minutes, maybe I could ask one thing. How much of this method and how much of the theory for the convergence and accuracy of the method depends on the symmetry of the metrics? What happens with matrices that are not symmetric?
Oh, you mean the coordinate method?
Yes.
Yeah, that's a very good question. So for the coordinate method, then if the matrix is not symmetric, then you need to use a singular value decomposition, right? So that instead of A minus XS transpose, we need to do something like A minus U V transpose. And then, so then you need to keep track of 2 vectors and so on and so forth, so that the problem is much more, tedious. But I think a lot of the theory, and I don't know about performance because we have never tried to do the singular value, but a lot of theory I think can be generalized to that situation as well.
All right. Okay. Thank you. Thank you. Okay. I see no more questions. Anyone who would like to ask? This is a final call for questions. All right. Thank you very much, Professor Lu. It was great. It was very interesting work. Thank you.
Thank you. Thanks. Thank you all for the attention, and hope you have a wonderful rest of the day.
Wish to everybody.